All right, moving on. So today we're going to continue to work on angles and angle measures and using angle measures for things. And today it's actually going to get a little bit more application oriented. In talking about using this idea of rotational angles and how we can apply that to circles. So a little bit of vocabulary here. When we're talking about a circle, we have things like a radius, we have a central angle, we have an arc length, and we have a sector area. And those pieces of a circle are often referred to in applications involving circles. So we need to know what that kind of vocabulary is actually talking about, so when we see it in a problem, we know what's going on and how we're supposed to set things up. Hopefully a couple of these are review, like radius. What is the radius of my circle?
Half of the diameter.
It's what?
Half of the diameter.
Half of the diameter. So what's the diameter of a circle?
It's like all the way across.
All the way across, and it has to go through the center. So all the way across like this is what we call a chord, but if it's all the way across through the center, we have a diameter. If we take half of that, then we're just going from the center out to the circle, and so that would be a radius. This would also be a radius. Any line that goes from the center out to the circle. Okay, easy enough. Central angle. What do you suppose we mean when we say central angle? It's kind of sound like. Use our context clues as opposed to Blue's Clues. You guys all the age of you remembering Blue's Clues? Hated watching that show with my kids. Anyway, central angle. What's it sound like? Angle at the center. What do you suppose has to be at the center? What part of the angle? Look like in the picture? The what? Yeah, so it's this angle, but what part of that angle has to be at the center of the circle? What do we call that? Come on, Geo. Dig, dig, dig. It's in there. I know it is. What do we call that point right there? The vertex. So a central angle is one where the vertex has to be at the center of your circle. So it's this angle we're talking about, which we can label with theta. Okay, arc length. What is an arc? I think we mentioned this last class, McKenna.
It's the outside of the circle.
Yeah, so it's a piece of the actual circle itself, and in this case, it's the piece, get this, that is subtended by the sides of the angle. That's a good word. I don't really know what it means, but it's a good word. The piece of the circle that is subtended by the sides of the angle. So in this case, we're talking about this piece of the circle right here, because it's being cut off from this side to this side just to get that length right there. Even though it's arc length, it is usually represented by an S, which can seem a little weird because then our next thing is called sector area. What is a sector of a circle? Or what do you think sector area is? The arc is a length. The arc is just this piece. It's like having a piece of string right there.
The area it's like.
Yeah, so it's this area of like the piece of pie, right? This kind of looks like a piece of pie, and so the area of that pie is what we call sector area. But the reason that's a little weird is because arc length actually starts with A, but we use S to represent it. Sector area actually starts with S, but we use A to represent it because it's area. So you have to make sure that when they're giving you information and they're just referring to it as S or A, that you understand which one you're really talking about. A is meant to be for area. So the area of that, piece of pie. Whereas S represents just that piece of the circle on the edge, kind of like the crust of the pie. Okay? So this is our A, right in there. Okay, everybody clear with the vocabulary? All right, so if I now label the circle with this kind of information, where I'm saying the radius of the circle is 5 inches, and the central angle of that particular sector is pi over 3. The question is, what is the arc length and what is the sector area? Okay? I want you two tables, so Tommy and the girls over here. I want you guys to see if you can just grunt it out. Like, can you just figure out from that information what that length would be? Okay? And then you four over here, I want you to see if you can figure out what that area piece would be. Okay? I want you to just see if you can figure it out based on the geometry that you know first. And then hopefully we'll use that to come up with an easier, more efficient way to get it in a minute. But see if you can figure it out just based on what you already know. Take a minute to do that. So just you four doing arc length and you four doing sector area. You can chat, you can share ideas, you can try stuff, you can use your calculator, figure it out. Think about what we talked about last class, if that helps. Use what you know about geometry. give it one more minute, try to figure out your respective answer, and then we'll see if we get. Alright, think you got it? Ready to give it a shot? Alright, arc length, folks. Somebody give us an idea. What would you do to figure out how long this part right here is based on what's labeled? Who would like to share? Say again? And how did you get it? The what other part's 3?
That central angle is like,
The central angle's pi over 3.
oh,
What's that?
That's a pi. That's a pi over 3.
oh, I was like just saying like sector 2.
No, it's pi over 3. It's a radian measure.
Never mind then.
Anybody else have an idea?
Well, pi over 3 is 1/6 of the entire circle.
Okay.
So then, if we find out the circumference of the entire circle, then we can just divide that by 6.
Okay, so how do I find the entire circle?
Pi r squared.
Close. If you're squaring something, are we talking about distance? No, we're talking about area. So we don't want the squared one, we want pi d, or 2 pi r. Yep. So I'm going to write it as 2 pi r, since r is what we have here. So if I put in the r, that's going to be 5. So I end up with 10 pi as the entire circumference. But then what do I do with that, Tommy?
Divided by 6.
Divide it by 6, because the pi over 3 is 1/6 of the circle. Okay, that's based on what we talked about last class. So for my sector, or sorry, my arc length, I'm going to take the 10 pi divided by 6 and reduce that down to 5 pi over 3. Okay, and what kind of unit should I put on that? Inches, because it was inches for our radius, and we're just talking about length, so it's going to be inches for our arc length. Okay, and for most things, unless it's actually part of a application problem, if you just want to leave it in terms of pi, that's fine. You don't have to get the decimal approximation for it. Okay, we're going to come back to that in just a second, but let's talk a little bit about sector area. So over here, what do you guys do to figure out the area of that piece? That part right there.
So the radian times sector area is pi r squared times x degrees.
Sorry, so pi r squared, and then what'd you do?
Multiplied by x over 360 degrees. And since pi thirds was 60 degrees, we just put 60 over 80 to 60. And then
Okay, back up a second. You lost me. Okay, so area of a circle,
it's pi.
okay. Do you want me to put anything into that yet?
Okay, we can put 5.
Go ahead and put the 5 in. So that's going to be like 25 pi, right? Okay, and then what do you want to do with that? Where'd you go from there?
And then I multiplied it by x over 360, and since the pi third is 60 degrees, it ended up being multiplied by 1/6, like in the first one.
Okay, okay. Didn't catch what you were saying there, but now I understand. So she's saying that this ends up being a 60-degree angle, out of the total 360 degrees of a total circle. That also gives us that idea of this being 1/6 of the circle. So if I take this 25 pi, 25 pi, and divide by 6 again, that's going to give us the area that we want. Clean that up just a little bit. Okay? All right, so going back to what we did. With our arc length, we said that we wanted to take the circumference of the circle, and then once we got that, we divided it by 6 so that we could end up with the arc length that we wanted. So what if we write all that out in one? Instead of doing it in pieces, let's say that I want to take my circumference and divide it by 6, which means taking 2 pi r and dividing by what I want to do? Yeah, divided by 6. Okay? Well, I can go ahead and simplify here and divide the 2 out to make this pi r over 3. And then I can separate those two and make it pi over 3 times the r separately. Well, where does pi over 3 come from in our diagram? Is there any relationship between the pi over 3 I got there and the pi and my diagram? Do you see a pi over 3 in the picture? Hello? Is there anybody out there? If we want to get through what we need to for our homework, you guys got to help me out here a little bit. I'm not going to tell you everything because you won't get it. Do you see a connection between the pi over 3 I got there and my diagram?
Yes.
Where? The central angle. So ultimately, when we're trying to find arc length, we really only have to do that. Arc length is simply taking our central angle times our radius if, and this is a big if, our central angle is in radians, which it was in this case. It was pi over 3. That's a radian measure. If we're given a central angle that's in degrees, then we need to use our conversions from last lesson to get it into radians first before we can use this formula. But this is the formula for arc length. It's very simple, and it basically just comes from what your gut tells you to do. Take the circumference, figure out what part of the circumference that we have, but when we actually simplify that out, what we ultimately end up with is just take the central angle and take it times the radius, you got it. Okay? Now, if we do a similar kind of thing with the sector area, we started out by saying that we're going to take our area of pi r squared and then divide it by the 6, because we had 1/6 of it. If we try to sort of pull this one apart, like we did this one, we kind of simplified and then pulled it apart to realize that, oh, we're really just dealing with our central angle and our radius. If I try to do that here, Did it quite work? Is pi over 6 the angle that we're dealing with? No. But is there a relationship between pi over 6 and the angle I'm dealing with? Like, can I do something to this to get this? Yeah, divide by 2, multiply by 1/2. So, what ends up happening is, regardless of what the central angle and the radius are, you always end up with this being half of whatever this is. And so we can end up then saying, I want to take 1/2 times my angle times the r squared, and that's going to give us our area formula. And again, this central angle has to be in radians. So these are really simple formulas as long as you're dealing with radians. You get degrees, you got to change into radians first. Okay? Everybody got that? All right. So see if you can answer those 2 questions based on that information now. Slightly new diagram. Want to know what the radius of the circle is and what the sector area of that section is going to be. And if you need to, you can just leave answers in terms of pi. You don't need to look them out. Just leave pi in the answer. Alright, let's see what happens. Aaron, what's the first thing you did? Finding the radius. First question.
So it's f is converted to 5 pi.
Okay, so in this case, we're being given a central angle, but it is in degree form. So the first thing we should do is change this into radians. So using our conversion, and you ended up with what? 5 pi over 9. Okay. What should I do from there? Peyton, what do you think we should do next?
I started with an equation, so I had like the arc length equal to, which is like 10 pi equal to 5 pi over 9 times the radius. And then I just
Okay,
solved-
so you use this one.
Yeah, and then I just solved for r.
So S was going to be the 10 pi, and theta is going to be 5 pi over 9, and then solve for r. Okay, so what do we need to do to solve for r?
Divide
Lucy?
by-
What do I do to solve that for r? Okay. So here everything cancels. That gets us our r by itself. What happens over on the left side?
Eight-
18.
no,
What?
It's like
Is it 18? 18.
Okay, because our pi's will cancel. They're just factors like any other number. We can cancel out 5 from each of these, which leaves us with a 2. And so you ultimately end up with 9 times 2, which is just 18. 18 what? Centimeters, because we're just talking in length, a distance. So 18 centimeters is our radius. Okay. All right, what about sector area? Harry, what'd you do for sector area?
I didn't get the full equation.
Okay, tell me how you set things up.
I didn't get the full equation.
Oh, you mean like the equation from the last, that one?
Oh, that's good.
So that's our equation. Okay, so now tell me what that should look like in this case.
So, fill in 18 for r.
So what was, now I have to remember. 1/2 theta r squared, right? Okay, so we're filling in 18 for r. That's going to get squared. What else?
The angle, you can fill in 5 pi over
5 pi over 9. And then we need the 1/2, right? Okay. So can I do some canceling before I start multiplying stuff out? I actually can, because look at what happens with my denominators here. What happens when I take a 2 times a 9? I get an 18. What's going on here? 18 is being squared, which means I have an 18 times an 18. So if I have an 18 in the denominator here, I can cancel that with one of the 18s being multiplied here. So basically my exponent goes away, and that cancels with my denominators. So I end up with then a 5 pi for the numerator. Whoop, nope, sorry. Go back. 5 pi from this numerator times the 118 that's still left from there, which ends up being how much? 90 pi. And what's the units on this? Centimeters squared, because we're talking about area. Okay, so our distance for radius does not end up having a pi in it because the two pieces that we knew, the arc length and then our angle in radians had pi's that canceled out. So we just ended up with a simple 18 for our distance, but when we find the area, the pi's not going to cancel out. We're going to keep that as part of the answer and just leave it as 90 pi centimeters squared, which ends up being about 270 centimeters squared. If you just round it off to a nice easy 3 for pi, we're talking about 270 centimeters squared, more or less. Okay, everybody okay with those? Now that you got the formula, we can use them. Okay, so along the same lines, a little more application oriented. So a fly lands on the end of the minute hand of our clock right now and rides on the end of the minute hand until it is startled. Until it is startled at the end of class. I think I meant to put the bell rings, but okay. So the bell rings, it's startled at the end of class, and it flies away. And the question is, how far does he sit there and ride? So right now, what time is it? 10:45? We're not quite at 5. 10:44. About right there. What time does class end? When's the bell gonna ring? What time? 11:25. So he's got to ride this minute hand all the way over to here. Okay, so that's the situation. What do I need to know to be able to figure out how far he traveled? Say again? The arc length. How am I going to find the arc length? What are the pieces I'm going to have to know to find arc length? Sorry? The central angle. Okay? So our central angle in this case is this thing. How am I going to figure that out? I don't know, is there a formula to figure out what that central angle is going to be? What?
Oh, no, just count.
Okay, so tell me, how would I figure out what that central angle is going to be?
It'd be 19 over 60.
Why?
It's 60 minutes.
Okay.
Oh, wait, no. It's,
I think it's gonna be 246.
It's going to be what? 246 what? Degrees? Why?
Because 360 degrees for a whole circle.
Okay.
So I divided that by 60 because there were 60 units.
Okay.
And then I multiplied that to 41.
Okay. Does that make sense, everybody? So we know that a full circle, in terms of rotation, is 360 degrees. We know that in the situation of a clock, going around the full circle is also equivalent to 60 minutes. So if we divide these two, goodness gracious, what all happened there? If we divide those two, then we can figure out how many degrees are in each minute. Okay? And then from 10:44 until 11:25, how many minutes is that? Take that times our 6 degrees per minute, we'll have what the angle measure should be. So how many did you say it was? 41? So 41 minutes, 246. Okay, and again, you can see how the labels work here. If I take this times minutes, and this was degrees per minute, minutes cancel out because we have one on top, one on the bottom. So when I multiply this, I end up with the 246, and the only label that's still left is the degree label. So now we're down to just an angle measure. Okay, so is that what I should use for theta? Why not? If somebody would say no. Yeah, so now we need to take that degree angle and convert it to a radian angle before we can actually stick it in for theta. Okay, so can I cancel? Divided by 2. Actually, I could probably divide by 6, right? That would get me back to this 41. And this would be 30, yeah? So 41 pi over 30 is going to be the radian equivalent of that angle. All right, so one piece of the puzzle down. 41 pi over 30. What else do we need to know? The radius. How am I going to figure that out? How are we going to figure out the radius? What is the radius in this case? Sorry?
The measurement for this, the vertex inside the top. So if it's one of those,
That's the radius?
wouldn't it be half a circle?
The radius is half a circle, half a diameter. But in this context, what would be the radius? The minute hand, right? So how are we going to figure out what our radius is? Measure the minute hand. Somebody grab the stool. Not sure if this is long enough or not. We can try it. If not, we have music. There's a stool under the blue table there. Grab it, bring it over, measure the minute hand. And do we want centimeters or inches? Inches? They want inches.
It's 6 inches.
Okay, now, did you see what she measured?
Yeah.
Is that what we want to measure?
Yes. No.
Not
I
quite.
can't see from the
Like middle to the side.
Yeah, middle, not necessarily the extra little bit. Yeah, so go from there out to your, I mean, you can still do it along the minute hand, but just instead of, you see what I mean? That where that brass middle is, yeah, do from there out to the edge rather than end to end, because that's actually our center. 5 inches, all right, thank you. All right, so we got a central angle of 41 pi over 30. We've got a radius of 5 inches. Figure out how far the fly is going to travel by the end of class. And do not leave this one in terms of pi, because that's not going to make any sense to me whatsoever. So actually get an approximate answer for this. Anybody got it? How far do you think you went, Aaron?
Approximately
21.5 inches. Anybody agree or disagree with that? You agree? You agree? Why don't I? I don't agree. Oh, I know why. Let me try again. Just a second. Okay. Yes, now I agree. Yes. I got that. Oh, for the computer? Quick, you need it. I'm not sure if it's the keyboard, but I have one over there. All right, so 21 point, what did we say, 5?
Yeah.
Inches. That's how far he would travel if he just sat there on the end of our minute hand from the time that we started until the time class ends. And so when you get problems like this, it's really just a matter of figuring out what piece of the situation represents radius, what piece of the situation represents our arc length, what piece of the situation represents our central angle, which of those do I actually have, which one am I trying to find, and then use your formula. And just make sure if you have measured something or you get information about something in terms of degrees, that you change it to radians first. Okay? Make sense? All right, let's take this to just one more level. So one of the things that comes up a lot when we talk about rotational kinds of angles is the idea of speed. And there's two different types of speed when you talk about rotation. There's actual linear speed, meaning how fast are you traveling kind of thing. But then you can also sometimes talk about speed in terms of angular speed. Okay? So I want to take a minute to talk a little bit about what the difference between those two is and use this example of a Ferris wheel to help us see how to work with that. So what we have up here is a Ferris wheel. And over top of the Ferris wheel, I have overlaid our 360-degree protractor again, so that we can see, if I change this, gotta do this first. All right, so our Ferris wheel is actually rotating around. We've got the little cars that are kids screaming, a whole bit. All right, so this is rotating around our 360-degree circle like a Ferris wheel would. When we talk about speed, if I were to ask you how fast is one of these cars traveling, what measurements do we need for speed? What does speed represent? Distance over time, okay? You guys all remember the delta symbol from chem, right? It means change. So that's what I'm saying here. So the change of distance, how far we went over the change of time, how long it took us to get there. Okay? And so we're going to try to figure that out for one of these Ferris wheel cars. And to do that, you're going to have to get some information from my diagram. So Tommy, if you could come over and join one of the two groups for just a minute. If you have 3 people in your group, I want one of you to be the Ferris wheel person, one of you to be the timer person, and one of you to be the recorder. If you only have 2 in your group, your recorder is probably going to be your timer. Okay? And so what's going to happen here is in just a minute, I'm going to start this timer. the Ferris wheel person is going to pick one of these cars, and as that car hits 0 here, you're going to say go. And when the Ferris wheel person says go, the timer person is going to say what number is on the timer. Recorder, write it down. And Ferris wheel person, you just keep your eyes on the Ferris wheel, and as soon as yours hits 0, you say go, and you follow it all the way around until it gets back to 0, and you say stop. Timer person, you're going to say what the time is at that point. Recorder, you write that down. And then figure out how much time passed in one full rotation. Make sense? So in your group, whoever your timer person is, you be the one that writes it down. Okay? Got it? So decide who's doing what. Who's going to do Ferris wheel, who's going to do the timer, who's going to do the recording. Okay, so our timer's running now. So whenever you're ready, Ferris wheel person, pick a car. When it hits 0, say go. When it gets back to 0, say stop.
I'll go on the next one.
No,
Go.
10 seconds.
Yes, sir.
Okay. Ready? Go.
Wait.
I don't think that's.
Yeah. Okay.
I'll follow it. I'll follow it. You see it. 3, 2,
Yeah.
1.
Yeah, yeah. I'm
Go.
sorry. I'll let you know.
Stop.
Okay, so everybody got it? So how long did you guys end up with?
I think it's 10 seconds.
How long did you guys end up with?
We had 9 seconds.
9 seconds? 10 seconds?
9
10 seconds? Okay. So depending on, we're going by seconds here. So whether it just flipped or it was about to flip again or whatever, between 9 and 10 seconds, okay? For the sake of easy, let's go with 10. Everybody okay with that? Oh, come back. So we've got change of time being 10 seconds. Okay? How are we going to figure out the distance that that car went in that amount of time? What do we need to know for that? Say again? Okay, and how big is the arc this time? The entire circle, because I asked you to watch it all the way around, right? So basically we need to find what? So that we can find the circumference, okay? So in the context of just this picture, we're going to find the radius. I think it's in here. Please be in here. Yep. All right, so let me move this down a bit so that it's on the. Oh, that's why. We'll move this down so it lines up with our diameter, and then we'll move this to the center, and we'll move this one to the end. Right there. That look okay? Center to end? Those two? All right. That is 4.6 centimeters. 4.6 centimeters. Okay? All right, so if we get this out of the way again. So if my radius is 4.6 centimeters, then what's the circumference? How much? 9.2 pi. Let's go ahead and multiply out the pi.
$28.9.
28.9? Okay. So 28.9, or let's say 29 centimeters. Okay? So, if I were asking you for the speed in centimeters per second, what would you say it is? Okay. 2.9 centimeters per second. You gotta get the idea. It's there. Okay, but here's the problem. I don't really know what centimeters per second is like. Like, is that fast? Is that slow? I don't know. So let's change it to something that does make a little more sense. Let's take our 2.9 centimeters per second, and let's figure out what that is in kilometers per hour. That's something I can get my head around. You tell me how many kilometers per hour we're going, I know whether we're going fast or slow. So, how do I change something like centimeters per second into kilometers per hour? Now, you may have seen this in science classes before. Amazingly, I got through high school having never seen this until I got to a college physics class. But there's something called data analysis, unit analysis, that helps with this. And with unit analysis, the idea is that you are going to multiply by conversion factors, and how you set up the conversion factor is based on the unit analysis. Meaning that if I ultimately want to end up with kilometers per hour, I have to set things up so that I cancel out labels that I have to end up with the label that I want. So let's start with the centimeters. What do I know is the equivalence between centimeters and kilometers? How many of one is in the other? $100,000? Because there's 100 centimeters in a meter, and then there's 1,000 meters in a kilometer. So you could go with 1 if you actually could come up with there's 100,000 centimeters in a kilometer. If not, then just set them up as separate conversion factors. Set up the one that goes from centimeters to meters first, and then set up the one that goes from meters to kilometers if you need to. Let's try to do it all as one. So, I am going to set up another fraction here that is basically 1, because I'm going to put the centimeters on one side of the fraction bar and the kilometers on the other side. I'm going to set them up so they're equivalent. So if my numerator and my denominator are equivalent, I'm just multiplying by 1. But which one I put on top and which one I put on the bottom depends on what I'm trying to cancel out. So if I'm trying to cancel out centimeters, which is currently on the top, then that means it's the centimeter measurement that I need to be on the bottom so that I can cancel just like I do with fractions. So kilometers needs to go on top, and 1 kilometer has 100,000 centimeters in it. This is what we call the conversion factor, because the top and the bottom are equivalent, but I set it up in a way that's going to cancel out labels for me. Okay? Then I do the same thing with time. So I'm starting with seconds. I want to end up with hours. Can you make that jump, or should we break it down? Can you tell me how many seconds are in an hour, or do we need to go by smaller steps? 3,600? Because there's 60 seconds in a minute, and then there's 60 minutes in an hour, so 60 times 60 would be 3,600. So which one should go on the top of this one? The 3,600? Because that is the seconds, and the seconds that I started with were on the bottom, so I need them on the top to cancel them out. That is equivalent to 1 hour. Whoops. 1 hour. There we go. So that's what's going to go on the bottom. Okay, so now if I can actually cancel out labels in a way so that all that's left are the two that I want in the order that I want them, then I know the numbers are ready to be worked out correctly. Does that make sense? So now I take 2.9 times 1 times 3,600, and then I divide that by the 100,000 that I have here. So do that quick, somebody on your calculator. Take 2.9 times 3,600, and then divide it by 100,000. So 0.1, what was the next couple? 0.1044. So at this rate, on my whiteboard, the Ferris wheel car is only traveling at about 1/10 of a kilometer per hour. That's pretty slow. Okay? Now, what if we did it for real? The original Ferris wheel is actually named after George Washington Gale Ferris, Jr. And the original one, which was built in Chicago for the World's Fair, World's Exposition that was going to be in Chicago, was about 80.4 meters in height. Okay, so let's say 80 meters from top to bottom. If we keep the same timing that we had with just our model on the previous slide, what would the linear speed of the car be now? So what changes in this? This is what we had to set up for this. What's going to change? Both? One or the other? Nothing? The distance, right? Our circumference is obviously going to change. We're saying the timing is going to stay the same. So we're still making one full rotation in 10 seconds, but how far we go is going to be different. Okay? All right, so for speed, we still want 10 seconds. But now what's the circumference of this Ferris wheel going to be? How much? About 251? And 251 what? Meters. So in meters per second, we're going about 25.1 meters per second. What would that be in kilometers per hour? So now what would my distance conversion have to be? 1,000 meters on the bottom for 1 kilometer. And time? That one's going to stay the same. All right, so multiply that out. 25.1 times 3,600 divided by 1,000. $90.36. So let's hope their timing wasn't the same as our model was. Because that would be whipping you off the Ferris wheel if you were going 90 kilometers per hour. That's pretty fast. Okay? But notice how it changed. Okay? Having a different size circle made our speed change because the amount of distance we covered in a certain amount of time changed. This is what we call linear speed. Because it's actually the distance, a linear kind of distance, even though it's going circular, that we're trying to cover in a certain amount of time. Okay? But then we also have this idea of angular distance. So an angular speed, let me try that again. Angular speed, not distance, can also be used to refer to how fast things are going. And so with angular speed, instead of the change of distance over time, we want to know the change of the angle measure over the change in time. So in this case, when you started a car here and you watched it go all the way around the circle and stopped right here, how much of an angle did you go through? You started here and watched it go all the way around. What's your angle measure in this one?
360 degrees.
360 degrees, or in radians. What's all the way around radians? 2 pi. Okay? So as an angular speed, we would be talking about 2 pi over the 10 seconds, which would be a pi over 5 angular speed. Okay, does that make sense? Because you went all the way around the circle in that 10 seconds. So in terms of the change in the angle over change of time, it's 2 pi over 10, which reduces to pi over 5. So what would angular speed be in this case? How much of an angle did we go through with this one? With the original? If I go 1 rotation with this original Ferris wheel, how much of an angle am I going through now? Still 2 pi, right? It's still just 1 rotation all the way around. And the change in time? Still 10 seconds. So what's the angular speed of my original size Ferris wheel? Still just pi over 5. which is why sometimes we want to talk about speed in terms of angular speed, because there are times where we don't want how big the circle is to affect how we're talking about how quickly things are happening. So if we're talking just in terms of change in angle measure over time, that has no bearing, or let me put it the other way, the radius or how big the circle is has no bearing on that. But if you talk linear speed, then your radius and the size of your circle does make a difference because it's going to change what that circumference is that you're trying to travel around. So a linear speed is going to change if the size of your circle changes. An angular speed, on the other hand, does not change based on size of circle, because it's all about really the rotation of it, not the circle it's creating. Does that make sense? So keep that in mind. There's going to be a couple of problems, I think one in particular on the homework, that are going to talk about speed. And just keep in mind that when you're talking angular speed, the size of the circle doesn't change your angular speed. When you're talking linear speed, it will. But angular speed doesn't change because of what it represents. Linear speed is the change of distance over time. Angular speed is the change of angle measured over time. Okay? All right, so that should be enough to get you through the 2.2b homework. It's about half of just kind of simple, if the radius is this and the central angle is this, what's your arc length kind of problems, and then half of more application kinds of problems, like the fly on our clock or the Ferris wheel or that kind of thing. Okay? But I think it's only like 8 or 10 problems total. 8 problems total. So that's going to be due for Friday. And then, trying to remember, double check on Canvas. We might have a quiz Friday. If it's not Friday, it's Monday. So double check, make sure that whenever it's coming up, you're ready for it. If there is a quiz, there should be a practice quiz in your book. So you can do that.
There is no practice quiz, so we don't have a quiz.
Yeah, probably. What's next?
2.3 notes for trig functions and part 1.
Okay.
And then it's 2.3. And then it's
Okay, so we got one more lesson in 2 parts, and then we'll take the quiz. Yep. So yeah, should be next Wednesday or Thursday actually. Thursday.
I just have a question. If it asks you to find the central angle of radians, if you use this equation,